This is finally here. Quantum approximate optimization algorithm explained. I've been waiting for these like for months. So Mihao, I'm super happy you got it done. Because I wanted to keep I wanted to kind of go back to these since it's been a while now. And as I really liked the VQE one that you did before, I thought that would be a good one as well. So there's a lot of stuff in here. I'm not going to try because I barely have 30 minutes today for this. Sorry, guys. But I want to try to get through this as quickly as possible. That's my style. And then go to Quirk, try to play with it. And then, I mean, we'll see how this goes. Ideally, go to StrangeWorks and get some of the stuff coded in there, playing with the concept. We'll see. There's a fair bit of introduction in here, so I'm gonna have quite some fun. Yeah, it looks like it's like half of this is introduction. Anyway, let's get started. So this is the second pause. The VQE one is here, by the way, for those who don't know. There's a really good one here. I don't know if this has been revisited because I see so the layout, some of the way this is rendered has changed. So it looks much nicer now with the gray box and all this stuff. But that was a really good article. It helped me really sort of crystallize some of the things around measurements, which I was really thankful for. So, what's the motivation behind this? How it works and what's good for? So, we'll go pretty deep into details. The motivation back here. Hey, child feeling this thing, something. Don't worry, you can for solving different problems for 2 years, and only recently started to really appreciate the math and the physics behind it. You can always come back and visit this blog post exactly. Combinatorial optimization problems. Evil aims sending notes in the classroom. So, imagine a classroom where students are sending notes between each other. Teachers knows exactly how many notes pass between each pair of students. The class is moving to a new room with a huge gap in the middle, preventing students from sending notes to the other side. How should the teacher divide the class into 2 groups in order to minimize the number of notes? So this is graph coloring, right? I guess. Or another example, in a faraway kingdom, kingdom merchants trading, should be which faction to maximize the losses. So what do both institutions have in common? They both can be described as the max cut. Sorry, not the coloring, but actually I think they are both somehow related. The max cut problem. It's the way you divide a graph into 2 groups, such as the edges going between the 2 groups have the biggest possible weight. The 2 groups, yeah. So in the first example, the nodes of the graph represent the students and the connection represents how many nodes that can pair students. The second example, the merchants are the node connecting the number to cuts, drachmals or talents. They're not mutual trade is worth. So this is the graph. This is the solution. Yeah, you see coloring, so you it's just graph coloring with 2 colors, I guess. Why max cut? A small digression here. If you've seen a portion of the graph in a different problem, it might not be the most obvious example. However, we use it for a few reasons. Max is a problem that the authors used in the original paper. It's the most well-suited example of QAOA application in the literature, probably because of 1. Solution max is a binary string, so just a string of zeros and ones. And there's no problem with encoding the results. Yeah. It's nice. As far as I can tell, it has some neat mathematical properties, especially for K-regular graphs, which make it easier to analyze. If you're interested, you can find more answers to the original paper, as well as other papers. There's some talks in here. Are those YouTube things? Oh, yeah, YouTube. So what do we have here?
So I'm going to talk about a quantum approximate optimization
Sorry for the volume. Okay, so this is
work I've done with my collaborators, Jeffrey Goldstone and Sam.
So this is a quantum approximate optimization algorithm. And sorry for the volume, guys. And so this is a
I'm actually going
new results. Okay, those might be worth checking later on. Why combinatorial optimization? So I guess discuss problems where you want to find the best solution from a finite set of solutions. It usually, yeah, that's kind of why also it's also the one that's used sometimes to kind of play with Grover's algorithm, because you can search just over all the different possible solutions. Ordering a solution, examples, traveling salesman problem, like knapsack problem. Yeah, this is the stuff where you put things on your backpack and you try to maximize something, right? The first problem is that as well combinatorial. This usually means that the number of possible solutions grows extremely fast. Exponential growth, exponential means that's not a problem in itself. In the case of continuous optimization, we have to deal with an infinite number of possible solutions since we use real numbers, and somehow we have efficient methods of doing that. The fact that we need to deal with discrete values actually makes things harder. That's interesting. Or at least different. Many continuous functions we have to deal with in optimization are smooth. If we change x just a little, also f of x also changes a little. And that's okay, that's kind of useful. Yeah, okay. So you can play with derivatives and integrals, I guess. That's what you mean is if we change only one bit of the solution from 0 to 1, get dramatically different results. It's also worth noting that many such problems are NP hard. Since was actually difficult to solve, why do we bother? Because they're applicable in so many places that we didn't try to list them here. Just listing out where you can apply. Really? Industrial combinatorial optimization. Interesting. QAOA introduction. QAOA is an algorithm which draws from various concepts. We'll start with a description of QAOA, and then we'll go one by one through all the pieces needed to actually understand why it works. Let's say a cost Hamiltonian representing our problem. We'll see how to create one in the section about Ising models. Cost Hamiltonian. So we can also construct an operator. Okay, we start with notation. Then we construct another operator, HB, where this is a Pauli X matrix, and corresponding to it, an operator. Okay, so this is okay. In QAOA, we'll construct the state. This is where P is usually called the number of steps, and it knows just how many times do we repeat applying. These S is the initial state, usually these or these, so zeros or plus, we call beta and gamma angles. So if I remember well, this is going to be something along the lines of kind of rotations. In order to find what the values of angles which produce a reasonable state, we do exactly the same thing as we did in VQE. We start from some initial parameters, measure the state, and update the angles to get a state closer. First time I look at this equation, I was like, oh, okay, let's implement it and see how it works. But the more I've been learning, the more I've started to ask questions. What do we need HB for? Why does HB have this exact form? Why do we use these funny operators? And predominantly, why should it even work at all? Let's find out the answers in the following paragraphs. Okay, so okay, so this goes pretty straightforward to Hamiltonians. There's no introduction to this, but I guess this is something that is explained in here as well. Hamiltonians, right? Yeah, it's a matrix that has possible energies of a physical system. So, okay. So that article kind of builds on top of that one, just because this is pretty, if you're kind of coming new to these, you're like, what the heck is that even? And then those things are rotations, I guess, right? So this is the this is the Pauli X matrix. It's a sum of the Pauli X matrices, sort of a. This I'm not so sure I understand why this makes sense or not. But let's go ahead. So adiabatic quantum computation. So that's the background. See, that's interesting because I remember I don't remember any of these things being put together somehow when I first started time evolution, touch, trutherization. Okay, I remember searching for these and not knowing what is it. And so let's say we have a quantum system described with a simple Hamiltonian with a known ground state. We also have another Hamiltonian, HC, whose ground state we want to learn. We can now construct a new Hamiltonian. Okay, so we have a simple Hamiltonian, HS, with a known ground state. And we have another one that we want to learn the ground state. So we can now construct a new Hamiltonian in the form of okay, HS plus HC. So it's the sum of both Hamiltonians. Okay, so it's a weight. Okay, so when alpha is 0, then it's just HS. When the alpha is 1, it's just HC. So this is a linear combination of those. The adiabatic theorem states that if we start in the ground state and very slowly start to increase alpha up to 1, then throughout the process, the system will always stay in the ground state of H, which means that at the end it will be in the ground state of HC. Yeah, it's also worth mentioning that alpha could be okay. So that's sort of something that we have to take as a given. So it's also worth mentioning that alpha could be an actual physical quantity. Of course, that's not an easy thing to do and certain conditions apply, but in principle, if the evolution is slow enough, we're able to find a solution to any problem if we can encode each solution in the ground state of HC. We use the word evolution for the process of changing the quantum system by changing alpha. Also, we often use alpha equals t divided by, where t is the current time and t is the total Rn time. So what this is saying is you try to encode the solution. So you try to build a Hamiltonian whose ground state is going to be a solution of your problem, but of course you don't know the solution of the problem. So what you do is you then combine these with, you build a Hamiltonian to sort of combining these with another Hamiltonian, the ground state of. And then you just let the system evolve. But that's pretty abstract, actually. Also, we often use alpha time, which means at the end will be ground state HC at the end of this whole evolution. Yes, but why does it matter that we evolve that step by step? So this is a physical quantity. So what is alpha? Increase. And why does it matter that we know H sub S? Let's see. So there is one big assumption in the previous paragraph which could easily ruin any potential usefulness of the method. If we can encode its solution in the ground state HC, well, if we don't know how to encode the problem, and then AQC won't help us. Fortunately, we know such encodings for many combinatorial optimization problems are, and we use Ising models to do that. Imagine a chain of particles. Each particle has a spin which is either up or down, plus or minus 1, and it wants to have a different spin than its neighbors. We can write down the Hamiltonian of such system like this. Here, this is this. So this thing, whatever it is, sub I is the spin of the ith particle, and that's all spins. Minus, minus, plus, plus, minus. String of all the spins. Okay, J is the strength of the interaction between the particles. This mathematical description usually works equally well with lattices instead of chains. Also, we can change the behavior of the system by changing the design, the sign of. If it's negative, it behaves as described. if it's negative, it behaves as described, but if it's positive, then the particles will try to behave to have the same spin direction. This model maps very well on quantum computers. We just need to change those things to Z operators acting on the ith qubit. It turns out that we can encode many different COPs, combinatorial optimization problems, using Ising models. I won't describe how to do that, but you can find many examples in this paper. For a description, it suffices to know that it's doable and that can do. Okay. Mm. Hmm. I feel a bit lost at the moment. I kind of feel like I understand, but I don't really see the sense of this or how does this connect or where is this going so far. But I mean, I've played with this before, right? I've played with the notion of the Ising models. It's just I'm trying to make sure that it just, I don't know, I'm just missing something. But it's me. It's not about the article. It's really increase. It's things kind of make sense, but I guess because they're kept at an intuitive level. I mean, I don't know. I'm happy so far, but I'm like, let's move on. Problems with AQC. So we can encode most problems of interest into Hamiltonians, and we have a method which basically guarantees that we find a proper solution. So what's the catch? In order to work, AQC requires to be very well isolated from the outside world, which is really hard to do in practice. It might require a very long time to run. To run it in a gate-based quantum, you won't be able to run it in a gate-based quantum computer. Well, while it is possible in principle, it will require much better hardware than we have today. So this is impractical in the foreseeable future. Basically, the harder your problem is, the more isolated your quantum system must be, the longer it has to run. Okay, so this may be the reason that doesn't kind of like catch, or I'm not kind of like feeling really attached to this, is because this is a diabatic quantum computation. So that has nothing to do with the gate model. And that's, I think I'm just approaching it with the wrong mindset at the right for that particular section. So we're talking about setting up a Hamiltonian. So we're talking about setting up a sort of a system, and we know how to prepare the ground state of this HS thingy here. And really, that's actually what these alpha 0 is the ground state of these. So we know how to prepare that. And if we know how to prepare a Hamiltonian, but we don't know the ground state, if we then make this combination and evolve this thing step by step, then we're going to get to that. That's kind of what the adiabatic theorem states, that if we start in the ground state of HS and very slowly start to increase this alpha, throughout the process, will always stay in the ground state of these. Okay. But what does it mean to prepare HC? That's why it's kind of a bit abstract. So the whole adiabatic thing here, maybe that's because this is the D wave people, right? Like, isn't that what they're doing? Okay, so I'll have to revisit that a bit. It just feels a bit fraying to me right now. Problems with AQC. Okay, relation to quantum annealing. So this seems like a good place to mention quantum annealing. The paradigm that can, okay, DOF is fine. The main idea behind QA is the same as for AQC. Start from a ground state of an easy Hamiltonian and slowly evolve your state towards the ground state of an interesting Hamiltonian. What's the difference here is an imperfect implementation of AQC, which trades some of AQC's power for easier implementation, although not everybody might agree on these, since the line between what the community call AQC versus QA is very blurry. We can say that QA is a heuristic algorithm, which can be more flexible when it comes to the rate of change between the two Hamiltonians, finite practical time, which is 100 microseconds in current devices, and operates at finite temperature. sum this up. Okay, so there's a bunch of comparisons in here and some stuff like that. Quantum mechanics background. And this is like the quantum mechanics, the evolution of quantum system, and Trutherization. There's an operator which is quite common in quantum computing. There's an operation which is quite common in quantum computing. Taking an operator A and creating another one of the form. But why we would do that? It comes from the Schrödinger equation. What it says is that the change in time of the state of a quantum system described by a time-independent Hamiltonian age depends solely on the form of this Hamiltonian. Nice. I'll have to reread this twice, I guess. And if we solve this equation, we see the dependencies. But I'm liking this. So this is the this is the okay. So that's the solution to the equation for t0. Okay. Oh no. Okay, that's okay. I get it. So what is that? If we take some state, so not t0. This is just the differential, right? Like the derivative. What does this tell us? That if we take some state and act on it, evolve it with a Hamiltonian age for a period of time, we will then get a state that is the state. If this sometimes imagine an electron orbiting the proton, hydrogen, the system is defined solely by the interaction between these two particles in their initial states, and we know how to describe the interaction. So if we the Schrödinger equation, we are able to get a formula describing the state of a system after time t. And if we do the math, we know it will look like this. The key point to remember, whenever you see an operator which looks like this, you can understand it as an evolution of the quantum system described by Hamiltonian age. But what does this Hamiltonian mean in terms of actual programming, of the actual gate? Is this something that you can implement with a gate model, this time evolution, or this is just something that happens naturally? Like you prepare the state and you just let the time pass, and then you just measure after a certain amount of time. Maybe that's it. That's what it means. So would these mean just prepare that and let it go and let it run for a while? See what happens. Is that what it means? I don't know. Because it's the evolution with time, right? So until this point, we've made one silent assumption. We assumed that the Hamiltonian we wanted to solve was time independent. But when we take a look at the Hamiltonian we use for AQC and change alpha for t, we cannot pretend it's time independent. Depending on how complicated this time dependency is, this might complicate the solution we've presented a little bit or a lot. In the later case, they are impossible to solve. Okay, so I'm probably, about the half. Let's just try to get a deal here. So what about Trutherization? Another concept important for understanding QAOA is Trutherization. Most of the time we want to find the ground state of Hamiltonian, which is too complicated for us to deal with directly. Then it might be useful to approximate it. An example can be surprise, a time-dependent Hamiltonian. To help us grasp the idea, we'll get back to the classical world. Imagine a curve. Let's say this curve is described by some function. We can approximate it by a piecewise linear function. The more pieces we use, the better approximation we get. Yeah, cool, nice. We can do the same with the time evolution of a quantum system for an operator. Yeah, okay, so it's actually shorthand for an operator. We can write these as a sort of a combination of those. The bigger n we use, the better approximation we can get. But keep in mind that time. Okay, so this is going to take probably another approximation particularly useful in quantum mechanics is called the Suzuki-Trotter expansion, a Trutherization. Or Trutherization is somewhat similar to other expansions we use in mathematics, like Taylor series expansion. If you're not familiar with this concept, I recommend watching the video 3 Blue 1 Brown. If our Hamiltonian has the following form, e to the a plus b, we can use the following relation. We can look at it approximating time evolution by a plus b, applying alternatively a and b for time intervals. So this is maybe gonna Okay, so this is now going to how can we simulate the effect of a Hamiltonian with time? Is it or is it not? This is what the angles are for, I guess. They simulate the changes in the Hamilton. I don't know. They simulate no. Maybe because that's not a gradient. We're not talking about gradient descent in here. We're talking about these angles, which are probably the trick. So do we have some context here again? Q creates a state. So that's the approximation where this has this form and this has this form. Correspond evolving this. So these states correspond to evolving the state with a Hamiltonian HB and HC for time beta and they are just happen to be translated to angles probably because that's the way you can parameterize gates. Several layers looks like a lot of Trutherization. So those are gates that simulate the evolution of the system. Okay, I get it. So you simulate the evolution of the system, and you expect to get to that point where sort of, I don't know, what do you expect out of these? What do you expect out of these? I think okay, so this is the, it looks like Trutherization combined two previous points. So here somewhat mimics adiabatic evolution from ground state to ground state HC, which encodes our solution. Remember Ising models. So answering the question in the previous paragraph could be given right. Choice of parameter is viewed as an approximation of AQC. Okay. So the relation, OSB important, circuit look like. Okay, cool. Oh, so that's kind of like, okay, I thought there'd be more into the actual, but this is really well put together after meet. I like it so far. So it kind of I think confused me a little bit, sort of right here in the middle. But I think those things start to make sense. I want to read it until the end, probably read it twice. What I want to do is I want to go through my previous videos about QAOA, see what I was thinking and doing by then, because I was a bit more like jumping right away to the circuit. See if I can answer the questions. Maybe we can do this. So let's see if we can answer this question in the next video. I'll try to answer these questions, right? So basically Mihal's questions. Why does this work at all, and all this kind of stuff. See if I can make sense of these from my perspective, and then read what's Mihal's take on this. But I really like the way this looks like at that point. Yeah. Okay. Not enough time for this today. It's a pity, but I'll definitely go through these tomorrow or on Wednesday. What does the circuit look like? Okay. Cool. I would have expected to be more details on the actual circuit, but let's see. Cool. Thank you.